Hello everyone, thank you for coming for the last presentation before the lunch break. I've been part of the Scientist Academy for the past 10 years, which makes me look a bit old, but I promise there is life after being 25. And I remember when I was sitting here both as a high school student and as a university student and listening to these interesting presentations, as my colleague mentioned before, wishing to be on the stage. Back in the day in high school, I was presenting about a different topic, but after that, later on, listening to all the Nobel Laureates and other students inspired me even more. So throughout the years, I've been participating in multiple research projects in my institute, which is the Institute of Surgical Research. I wanted to be a surgeon, but then later on, I got more experience and I became smarter. So my research topic is still connected to surgery, which is the development of a kidney transplantation model in a porcine large animal way. Today, I want to talk about the method and the mitochondrial involvement following methane perfusion. So, end-stage kidney disease is the last stage of renal failure. This affects approximately 100,000 people per year, and it can be treated by either dialysis or kidney transplantation. Dialysis is widely available and it's easily accessible. It's a non-surgical procedure, but it's very time-consuming and it offers a lower quality of life. Kidney transplantation, however, offers a higher quality of life and higher long-term survival, but it's a surgical procedure, and it can come with complications like rejection and immune reactions. These immune reactions are caused by ischemia reperfusion injury, because during the process there is warm and cold ischemia. Ischemia means that the tissue is deprived of oxygen and nutrition, and it can lead to delayed graft function and primary graft dysfunction. So our institute, we decided to go with a pig model. It's called a porcine model, which has advantages and disadvantages, of course. The advantage of a porcine model is it really closely mimics anatomical and physiological properties of a human, so it's easy to translate to clinical studies. It's readily available and it's cost-effective, of course. The disadvantages are really minor compared to these. Porcine model is more susceptible to malignant hyperthermia, cardiac irritability, and peptic ulceration. I will mention these later on in my presentation. So, kidney transplantation is a surgical procedure, and after removing the kidney, it goes through static cold storage in a solution called HTK. During this cold storage, the cold ischemia leads to ATP depletion, cytochrome C release, and reactive oxygen species release. This causes mitochondrial dysfunction and can lead to the transplanted kidney damage. So, in our experiment, our goal was, first of all, to establish a large animal model that closely replicates human surgical conditions and accurately mimics the cellular processes. This would allow a detailed study on ischemia reperfusion and later therapeutical studies as well. Furthermore, our institute is very largely specializing on methane and the study of therapeutical usage of methane. So in our case, we were curious about how methane can be implemented in kidney transplantation and infusing in the HTK solution. The exact effect of methane is not clearly understood. It's considered a bioactive gas like nitrogen monoxide. You might have studied about the effects of it. So in our institute, we are curious about the therapeutical effects, but of course we are trying to map out how it exactly is forming these effects. So throughout our experiments and other topics that we explored, we saw that methane can improve mitochondrial function, it has anti-inflammatory effects, it has antioxidant and anti-nitrosative effects, and it can improve microcirculation and be anti-apoptotic. The exact mechanism, as I mentioned, is not clear. It dissolves in the membrane, and maybe it has an effect on transmembrane proteins, ion channels, enzymes. It can affect the membrane integrity, but the overall effect is an organoprotective effect that we've seen study after study. So for our experiments, we used Vietnamese mini pigs, and it was an auto-transplantation model, meaning that the transplanted organ was coming from the same animal as it was implanted in. Throughout the experiment, the animal was ventilated and anesthetized, and we measured renal artery flow, hemodynamical parameters, and tissue parameters like urine and blood. Before the operations, we created two groups by infusing methane with 5 liters per minute flow for 15 minutes in an HTK solution. So we had the two groups with a methane-enriched HTK solution and a baseline group with nothing added to the solution. Our experiments are one of a kind in a way that they take 3 days. On the first day, we remove the kidney, and after that, the kidney is stored for 24 hours in either solution. And on the second day, we invite the surgeons back, and the second surgery happens by implanting back the kidney. After that, there is a 24-hour intensive monitoring period where we measure different hemodynamical parameters, urine, blood, and at the end of the experiment, we take tissue samples. So here you can see the kidney extracted, and we used HTK solution, which is a standard clinical practice, to infuse and perfuse the kidney throughout, cleaning the tissues from blood, which is important before a long-term storage placement. HTK solution is used in Europe and Asia mostly, and here you can see that we put the solution through, perfuse it through the tissues, through the renal artery. After that, we put it at 4 degrees Celsius for 24 hours, and the next day, we take it out and resume the experiment. So the warm ischemia happens right after the kidney is cut off from the central circulation, when the warm blood stops going through the organ. Then, after washing through with the HTK solution, it enters cold ischemia, which reduces metabolic demand. But metabolic demand is still present, so each hour passing by increases the risk of tissue damage, and when implanted back into the animal, it can cause real issues. So for our experiments, we used the kidney, both the medulla and the cortex, and then this was homogenized with Potter homogenization. That's destroying the cell membrane but keeps the mitochondrial membrane intact. So after that, we can measure the mitochondrial activity of the kidney. We used high-resolution respirometry, which is by a company called Ouroboros. It's a new technique introduced in the past decade. And it offers us a real-time measurement of the mitochondrial activity. Here you can see what we see during the experiment as well. You might not know the exact mechanism of how ATP is generated in the mitochondria, but basically, throughout the processes, there is the baseline, and there are many complexes in the mitochondria that at each step produce ATP. But with the high-resolution respirometry, we can look at each complex one by one by adding different substances. So, after measuring the kidney the tissue of the kidney, we reached to some of the dry evidence that I'm going to present, but I'm going to explain each step and what we saw with it. So, first of all, we measured the baseline to differentiate the methane and the non-methane groups, and obviously there is no significant difference between the two. So the first data that we looked at is the respiration of complex 1 after substrate induction, meaning we looked at the complex 1 of the mitochondria, which didn't show any difference either between the two groups, so it probably wasn't really affected. But looking at complex 1 and complex 2 dependent OXPHOS, which is oxidative phosphorylation capacity, meaning the capacity to produce ATP by these two complexes, which is, of course, very important for the mitochondria. That's the function of the mitochondria. We saw that by adding methane to the H3K solution, there was a significant increase of ATP production in both the cortex and the medulla. That's a significant improvement in the kidney tissue, damaged tissue. Complex 4 activity was only increased in the medulla of the kidney, which was an interesting finding. And furthermore, we looked at a test called cytochrome C test, looking at the integrity of the mitochondrial membrane. And here we saw significant decrease in the methane induction as well, looking at the transport chain reactions and the integrity and how much solution can go through the membrane. So overall, looking at the mitochondrial data, we saw that complex 1, complex 2 linked oxidative phosphorylation capacity was improved. Complex 4 activity was improved as well, and the cytochrome C test showed a better mitochondrial membrane integrity. So concluding the mitochondrial aspect of our study, we saw that methane decreases static cold storage-induced ischemia. Thus, there was a decreased organ dysfunction, and an intact outer membrane was observed by the cytochrome C test. So mitochondrial homeostasis was maintained during static cold storage. Now I want to segue into some of the complications that we faced. It might be a bit more interesting on a surgical aspect. So as we used a porcine model, there are anatomical differences. Even though that is closely mimicking a human's body, these differences can pose a problem for us because we use a normal operating theater for our studies, which are designed for humans. So one of the first problems that we face that the abdominal cavity is much deeper in the animal, and after an abdominal surgery, strangulation can happen. This is called intestinal necrosis, and this is the necrotic tissue of the intestines. This happened a few times during the surgeries, and it was we try to prevent it with different ways, but it's an anatomical difference. So monitoring the animal was key in this aspect. The surgeons faced a different problem, so they were trained obviously on human kidney transplantation. So facing a porcine model, they faced some differences like a double or multiple renal arteries. We wanted to offer them a solution by introducing ultrasound before the surgery to look at different anatomical aspects of the animal, which is used some days. Thirdly, one of the most important problems that we can face during the surgery, but it happens in a hospital setting as well, is the reperfusion of the kidneys. So after static cold storage, when the kidney is reintroduced to the circulation, the normal reaction would be to pink up and start to produce urine right immediately. Here you can see a positive example of it. So after releasing the clamps and the arterial blood flowing through the kidney, the tissues became pink and we noticed dripping of the urine. This is the problem that some of the experiments failed at. It wasn't successful. So after releasing the clamps, some of the tissue became pink and viable, but some became necrotized and died off. Obviously, these kidneys are not viable, and the transplantation is not successful in this case because we lose the graft, we lose the kidney. So monitoring the animal was very important. It was a 24-hour shift for us with a team of students, researchers, and medical doctors, surgeons, and anesthesiologists. And it was key because hourly we measured parameters and took samples. So the take-home message, because we got this question a lot, why don't we use smaller animals which is easily replaceable, for example, rats or mice? Using a porcine model is still preferable in surgical research because of the advantages that I mentioned previously. Although complications, anatomical differences, and staff error can still happen, these experiments are very complex to organize, but it's very rewarding to see a closely mimicked study of a process that can happen in a clinical environment as well. So thank you for your attention and listening to my presentation, and I hope you have some questions in the lunchtime for me.
Very much for this very nice talk. Really inspiring.